The bridge was carrying the crowd. Then the crowd became part of the machine. The sideways opening. On Saturday, June 10, 2000, a new pedestrian bridge opened across the Thames and immediately began doing something its designers had not expected. Under the opening day crowd, parts of the deck moved from side to side. Video showed people widening their stance, grabbing rails, and adjusting their gait. The bridge's engineering team later reported lateral movement of as much as 50 mm in the south span and 70 mm in the center span. The north span did not move substantially. Those numbers describe displacement, not a claim that collapse was imminent. The established failure was serviceability, motion severe enough to make normal crossing uncomfortable and difficult. Officials limited access, then closed the bridge on June 12 for investigation. That distinction matters. A bridge can remain strong enough to carry its loads while failing at the equally real job of feeling stable beneath people. The opening had revealed a feedback problem between a lightweight structure and the moving crowd placed on it. A bridge designed to disappear. The bridge was intentionally slender. Its suspension cables run beside the deck rather than rising into tall towers, producing a shallow profile across 3 spans. That elegance also meant the structure was comparatively responsive. Every bridge has natural modes, preferred shapes and frequencies in which it moves when disturbed. Designers already check familiar effects such as wind, vertical footfall, and groups marching in step. The unusual opening day response was lateral, horizontal, and across the direction of travel. Ordinary walking applies smaller side forces than vertical ones, so the design practice of the time did not fully capture how a dense crowd could interact with a laterally flexible deck. This is not evidence that slenderness itself was defective. It set the physical stage, low inherent damping and lateral modes in a frequency range that people could feed. The missing part was a reliable load model for that human structure feedback. The crowd was not just weight. Once the surface moved, people became active participants in the motion. What a walking body does. Walking looks forward, but balance is managed sideways. As weight transfers from one foot to the other, the body's center of mass shifts. On fixed ground, each foot lands where it can arrest that small fall. On a deck sliding laterally, a pedestrian naturally changes foot placement to remain upright. That correction pushes back on the deck. The original investigation described the effect as synchronous lateral excitation and observed that, above a crowd-dependent threshold, lateral force increased with bridge velocity. A popular retelling says everyone simply marched in perfect lockstep. That is too neat. Later peer-reviewed work by University of Bristol engineer John MacDonald modeled pedestrians as balancing inverted pendulums and showed that random pacing can still generate a force component correlated with bridge motion. In that description, people act like negative damping. Instead of removing energy, their balancing response can add it. Researchers continue to refine the exact biomechanics. The established point is narrower and stronger. Movement changed pedestrian forces, and those forces amplified particular lateral modes. The feedback loop. Imagine pushing a playground swing. A small shove at an unhelpful moment does little. Repeated shoves timed with the motion build a large response. The bridge did not require one person to deliver a dramatic push. It required enough small lateral forces to add energy faster than the structure naturally dissipated it. A slight deck movement prompted balance corrections. Some component of the crowd's force aligned with the movement. The deck then moved more, which demanded larger corrections. That loop could cross a threshold as pedestrian numbers increased. Engineers found significant opening day motion in lateral modes near 0.5 and 1 Hz, slow enough to interact with side-to-side walking dynamics. Calling the event simple resonance is incomplete because the loading itself changed in response to the bridge. It was a coupled system, structure plus pedestrians. Nor did every span respond equally, because modal shapes and local crowd conditions differed. The center and south spans displayed the major movements, the north span did not. The incident turned a vaguely known footbridge phenomenon into an urgent, measurable design problem, turning a crowd into data. After closure, the team did not begin by making the bridge heavier or stiffer at random. It instrumented the structure, measured its modes and damping, studied opening day video, and ran controlled tests with pedestrians. The aim was to identify which modes were vulnerable, how force changed with deck velocity, and how much additional damping would prevent the feedback from growing. This was a system identification problem. A mathematical model had to reproduce measured behavior before it could guide a retrofit. Controlled groups also allowed investigators to separate ordinary random footfall from the force that emerged after the deck began responding. That distinction turned an embarrassing public symptom into a repeatable engineering observation. The measurements showed that crowd size alone was not the full variable. The number of pedestrians contributing force to a particular moving mode mattered. Tests helped establish a critical crowd relationship. Below a certain participation level, natural damping could absorb the input; above it, response could grow. The team then evaluated possible fixes. Extra bracing or major structural alteration risked changing the bridge's defining appearance and could be inefficient across multiple modes. Passive damping offered another route. Instead of preventing all movement through brute stiffness, devices could take energy out of motion as it began. The solution would need to work for tiny oscillations, survive enormous numbers of cycles, and fit into very limited space around the deck and supports. The shock absorbers. The first family of devices was fluid viscous dampers. Picture a piston moving through a sealed cylinder. As the bridge and its supports shift relative to one another, the piston forces fluid through controlled passages. Resistance converts mechanical energy into a small amount of heat. The action depends on motion, so it can suppress oscillation without rigidly locking parts that must still accommodate temperature, wind, and ordinary load changes. Placement was difficult because the bridge's lateral modes did not create generous movement at every convenient attachment point. According to the damper manufacturer's technical account, the units had to respond to movements as small as 0.025 mm and endure a design life exceeding a billion cycles. Engineers arranged dampers in several geometries so deck movement produced useful stroke in the devices. The reported goal was roughly 20% of critical damping in the relevant lateral modes, far above the bridge's original inherent damping. In plain language, the feedback loop would lose energy before the crowd could build it. Masses that move the other way. Viscous dampers were not the whole retrofit. Engineers also installed tuned mass dampers for selected lateral and vertical modes. A tuned mass damper is a deliberately mobile weight connected to the structure by springs and damping elements. Its frequency is adjusted so that, when the deck begins moving in a target mode, the auxiliary mass moves out of phase. The reaction force opposes the deck's motion and draws energy into the damper. This is not a universal counterweight; tuning matters. One unit is most effective over a chosen frequency band, so multiple devices addressed different modes. The combined strategy was elegant. Fluid dampers supplied broad, velocity-dependent energy dissipation for lateral movement, while tuned masses targeted resonances that needed additional control. Government procurement history for the bridge confirms that both viscous and tuned mass dampers were added before reopening. The fix preserved the shallow suspension concept. Rather than disguising the bridge as a much stiffer structure, engineers changed its dynamic behavior, how quickly motion decayed and how strongly a walking crowd could excite it. The test that closed the loop. A corrective design is only a hypothesis until it survives the condition that exposed the problem. The manufacturer's technical paper describes final proving trials with about 2,000 people walking on the modified bridge. Instrumentation compared the response with predictions and showed that the added damping suppressed the problematic motion. The bridge officially reopened on February 22, 2002. Its most important legacy is not the nickname it acquired. The incident forced pedestrian bridges to be treated as human structure systems, with lateral vibration and comfort checked explicitly rather than assumed harmless. Later research refined the mechanism from a simple story of synchronized footsteps toward balance-based models and negative damping. That evolution is healthy engineering. Observations remain fixed while explanations improve. The payoff was also physical and inspectable. Pistons dissipate motion. Tuned masses oppose selected modes. Tests verify the combined system under crowd loading. The safer process is the complete chain: measure the real response, model the feedback, add damping, and prove the modification at scale before returning the bridge to service.